Hello guys, in today's video we're gonna see what a dense set is and what a separable space is. So we start our discussion with the formal definition of a dense set. So I say a subset M of a metric space X is said to be dense in X if the closure of M is equals to X. If my subset M satisfies this property, then I say that my set M is dense in my metric space X. And now we see what a separable space is. So by separable space, I mean that X is said to be separable if it has a countable subset which is dense in X. Now the important thing here to remember is the fact that this should be countable. The subset should have a countable number of elements. And when a metric space X has a subset M which has a countable number of elements such that the closure of M is equals to X, then I say that my space X is separable. Okay, so now we delve into the proof of why L infinity is not a separable space. Let's check that proof. So I start with defining L infinity as before. It's the space of all bounded sequences. So this is a sequence, as you can see, and the supremum of any single element of the sequence is finite. So therefore I can say L infinity to be the space of all bounded sequences. Now consider all sequences for which xn is either 0 or 1. So let us write a few sequences like 0 or 1. So 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. Similarly, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. So there are uncountably infinite number of such sequences. Uncountably infinite. Why uncountably infinite? How do I know that this infinity of sequences of the kind 0, 1 are infinite? Is because we have to go back to our linear algebra lessons or maybe even yet elementary stuff. So there's a concept that every real number, so let me write it down, every real number between 0 and 1 can be represented in binary format, can be represented in binary with these kind of formulas, these kind of. If you just go and do a quick Google search on how to represent real decimals between 0 and 1 into binary numbers, this is exactly the kind of numbers you would get. So this number corresponds to a real number between 0 and 1. And every real number between 0 and 1 can be written like this in the form of binary numbers. So the number of real numbers between 0 and 1 are uncountably infinite, and that is why I can say that sequences of the form 0 and 1 are uncountable. There's a total uncountable number of elements in such kind of sequences. I hope I made the point clear. So till now we have just discussed that L infinity is a sequence space, and we take a subset of L infinity such that the elements in the sequences are either 0 or 1, and then we prove that the total number of sequences of such kind where every element is either a 0 or 1 are uncountable. It's an uncountable infinity. And why we know that is because every real number between 0 and 1, if we convert into a binary form, can be represented like this. And if it can be represented like this, then we know that the total number of real numbers between 0 and 1 are uncountably infinite, and that is why this sequence is uncountably infinite. Okay, now take any two different sequences of this kind, S1 and S2, and then we want to find out the infinity norm of two separate sequences like these. So I want you to focus very carefully that the next thing we're gonna do is really important to a concept. So if I have two different sequences, again, these sequences only contain 0 or 1. And I want to take the infinity norm of these. What do I mean by infinity norm? So if I have a sequence S1 and I take a sequence S2 and then I subtract the individual elements of the sequence. So suppose this S1 is like 1 0 1 1 0 0 1 0 0 1 blah blah blah, and again this S2 is 0 1 0 0 1 1 1 1 1 1 0 blah blah blah. Now what I do when I take the infinity norm is I take the individual elements and I do the subtraction of them. So 1 minus 0 is 1, 0 minus 1 is minus 1, and so on. Okay, and once I do that, and then I take the infinity norm of this. So infinity norm means the supremum norm, and the supremum norm of all of these elements could be nothing but 1. You see, because if I subtract any two elements, this is what I got. And if I wanted to choose the supremum out of all these elements, what are these elements? 0, 1 and minus 1. If I want to choose the supremum, then of course 1 is the supremum between 0, 1 and minus 1 as far as I know. So again, what did we get? We did get that if we take two separate sequences in our space L infinity of the form 0 and 1, then the distance between two sequences is 1. So let's try to draw a picture of it. So this is my sequence space, okay? And now let's have L infinity, and now what I have is these points, okay? This is a sequence, okay? This single point is a sequence. This dotted curve around is something else. I would explain in a short while. So if I have one sequence here, one sequence there, another sequence here, another sequence here, another sequence here. But the thing to notice about all these sequences, no matter what sequences we take, is that the distance between any two sequences is equal to 1. Okay, so distance between this point and this point is 1. Okay, where each of these points is an infinite sequence. So in order to simplify things, this is an infinite sequence, not a single point. Okay, so I have these infinite sequences and the distance between them is 1, as we saw from here. And now what I do is I take a ball of radius 1/3. So if I draw a ball of radius 1/3 around each of my infinite sequences, I have an uncountable number of balls. So once I have that, I go back to the definition of a dense set, what it meant for a set to be dense or a space to be separable. I say that, okay, X is said to be separable if it has a countable subset which is dense in X. Okay, this was my definition. Now let's go back and play with this definition for a while. So I should have a countable subset which is dense in X. So let's do one thing. Let us start with a set. Let us start with a set M. Okay. Now suppose M is a dense subset of L infinity. So suppose, now what I want to show is that M closure is equals to L infinity. And now I say that X be an element of M. And as I saw before, so one of the definitions of separability is that, okay, I should have said it. while giving the definition of separable spaces. So before I resume, let me give an example so that the case is cleared. So I say that the set Q of all rational numbers is countable and is dense in R. So I say that real number, real line is separable. So in order to show separable, R-A-B-L-E, so in order to show this point, I need to show that there is a M which is countable, which is a subset of R, such that closure of M is equals to R. Now, an intuition behind this closure of M is equals to R is that I can approximate any point on R. So let me write it down as well. Approximate any point in R with any degree of precision. So any degree of precision epsilon with an element from M. So if I have a set, in this case the real number line, let us denote it by X for notational convenience. So I have the set X, and any element in the set of real numbers can be approximated with any degree of precision with an element from the set of rational numbers. And I know that this set of rational numbers is countable. Rational numbers are countable. This is analysis 0. And I can approximate any X or any element in X with any element from M with any degree of precision epsilon. So let's look it back again. You give me an element from R and give me a value or a number epsilon. Say epsilon is equals to 10 to the power minus 20. So I want to find a point within the range of 10 to the power minus 20 in R, and if I can do that with my set of rational numbers, I say that the real number line R is separable, and I say that the set of rational numbers Q is dense in R. Okay, so now coming back to our case, we had L infinity space, and then I said, okay, suppose M is a dense subset of L infinity. And now if M is a dense subset of L infinity, so now the case in hand is, till now I have defined that this is my space L infinity, and these points are separate sequences, and the distance between any two elements is 1. And now I say that suppose M is a dense set of L infinity. Now that means I can approximate any element in L infinity by a point in M. So that is the exact definition of being a dense subset, that M closure is equals to X. Suppose X is the set of real numbers and M is the set of rational numbers, then I can write it at this, that okay, M is the set of rational numbers and M closure is equals to X. So similarly in this case, I take a dense set, okay, in L infinity, which means that I can approximate each of these points in L infinity with arbitrary degree of precision epsilon. So this epsilon can be as small or as big as you want, but in this sense I'm looking for small epsilons. So I can take any element in my set M, and if I have an element in X, then I can approximate it with an element in M with an arbitrary degree of precision. So you give me L infinity, you give me a X tilde in say L infinity, and along with that you give me an epsilon. You give me an epsilon, you say, okay, find me a number such that that number belongs to M and such that X minus, suppose this is small m, is less than epsilon. So this is what we want, okay? Now, what I did was I assumed that there is a dense set of L infinity, and that means I can approximate any element in L infinity with a point in M, but that must mean that I can find in each of these infinite number of balls. So though I drew this diagram, in each of these infinite number of balls I can find an element of my M, which means that this dense subset that I chose has an uncountable number of elements. Why uncountable? Because the balls which represent the sequences or a ball around the sequences were infinite because there were infinite number of sequences. And now when I want to say that a set M is dense in L infinity, I can say that in each of these balls I can find a point in M which lies in each of these balls. But since these balls were uncountably infinite themselves, the number of elements in my set M has to be uncountably infinite too, which means that my assumption, that my definition, X is separable if it has a countable subset which is dense in X. But in our case, we have an uncountable subset, which means that my space L infinity is not separable because every dense subset is uncountable. See? And that's why space L infinity is not separable. So now I'm going to talk about why my space LP is separable. If you go to Crisis, you can find it on page number 23. The proof is very abstract and disorienting, I assume. And that's why I came up with a neat, quick and shorter proof. So we would try to understand things in a conceptual way, in a more generalized way. So let LP be my set. Okay, so LP is my space, and I want to prove that this space is separable. So going back to our previous definition, I saw that X is separable if and only if there exists a countable M which is a subset of X such that M closure is equals to X. And another definition of separability is, this is the first definition. The second definition, you can also say that there exists a countable S which is a subset of X with the span of S is equals to X. So this is my definition of separability. I can say that X is separable if I can find either one of these two cases. And trying to understand it more abstractly, I can say that A is separable if it consists. So if I have a set A, I say that it's separable if there exists a subset B such that B can approximate. So if I take any element A belonging to A can be approximated to epsilon, to a degree of precision epsilon, such that A minus B is less than epsilon, where B belongs to my capital B. So this is the basic definition of being dense in a set. And now we return to a case of LP. Now what I want you to focus on is that I have a linear combination of elements, okay? And I want to show that LP is separable. So I take any epsilon greater than 0 and I take a sequence in LP. Okay. Now the very characteristic of any element in my LP space is that the p norm is less than infinity. So I can write it as summation n is equals to 1 to infinity xnp is less than infinity. Now I know some of you are raising their eyebrows saying that I should do like this and hold to the power 1 by p. Well, this definition is also correct, but if I just get rid of 1 by p, then also it all makes sense. So for the sake of proving this theorem, I would just think that, okay, a sequence xn is an LP. It means that this quantity here, you see this quantity, use a pen, this quantity here is less than infinity. Now, or in similar terms, I can also say that there is this sum converges. If this sum converges, then so there exists a capital N belonging to my natural number such that, so I say that a sequence converges, this sequence converges if the summation of terms from n equals to 1 to infinity minus summation of a finite number of terms is less than epsilon. So I give you an epsilon, or let's say you give me an epsilon, you give me an epsilon 10 to the power minus 30, say. And then if my series is a converging series, then I can say that, okay, I will give you a value of n. Let this value of n be 10,000, 10 to the power 6. So I can say that if the series converges, then the sum from n is equal to 1 to infinity x and p minus sum from n is equal to 10 to the power 6 x and p is less than epsilon. So you gave me an epsilon. You said, okay, my epsilon is 10 to the power minus 30. Then the difference between the summation from n equals to 1 to infinity and n equal to 1 to 10 to the power 6, say, is less than epsilon. So for every epsilon, there exists a n such that this quantity here is less than epsilon. If this exists, then I say that my series converges and vice versa. So since my series converges, I can write it in this way. And this is nothing but equal to the summation of n is equals to n plus 1 till infinity, which comes out to be x and p. And since it's less than epsilon, I can also tweak my definition a bit and I can say that it is less than epsilon to the power of p. Because remember, this epsilon is in my hands. I can do whatever I wanted with it. So, okay, till now it's proven that this thing is less than epsilon p. Okay, now I construct this sequence. Okay, now I construct this sequence. And which is this sequence? The sequence looks something like this. Okay, so here is x1, x2 till xn, and every other element of this sequence is nothing but 0. And now I say that, okay, now close your eyes for a sec and imagine that I'm talking about a 3-dimensional vector 1, 2, and 3. And if I give you a 3-dimensional vector, I want you to write it in a spaces forms. How would you write it? You would write it as 1 times 1, 0, plus 2 times 0, 1, 0, plus 3 times 0, 0, 1. This is how you would decompose it into a set of eigenvalues and eigenbases, right? So again, consider this infinite sequence to be a vector of infinite length. And if I have forgot to mention before, those e's that I mentioned, these en's are nothing but e1 is something like 1, 0, 0, 0, 0, 0, and E2 is like 0, 1, 0, 0, 0, 0. It's very similar to our case in finite dimensional analysis, where you see that the value of 1 corresponds to the index that E has. So if the index is 2, then the value of 1 would be at the second position, and so on. Now I have these as the basis, okay? And if I have any sequence, so if I have any sequence of length infinite, okay, this is an infinite sequence of length infinity, and now think of this as a vector. And now just in the case below, or just in the case above, I wrote this vector as a sum of these. So similarly, I can write this as this x1 e1 plus x2 e2 plus xn en plus 0. Now when I decompose it into this form, I can see that when I take the norm of this, so if I take the norm of this from any element in LP, so I had an assumption before that xxn was an element of LP, this belonging to LP. So in this case, I can say that let me take the difference of this infinite sequence with this. I want to take the difference of these two different elements. And how would I do that? I take the p norm of both of them. So let me write it like this: xn, where n goes from 1 till infinity, minus x1 e1 plus x2 e2 plus x3 e3 plus xn en p norm. I take the p norm of these two things. And now I see that this is nothing but, so this is summation from 1 till infinity, and this is summation from 1 to n. So this would nothing be the summation from n plus 1 till infinity. So I can write it as all of these things would be 0, the summation till n's would be 0, okay, and then I start with n plus 1, so I can write it as like this: xn plus 1, comma xn plus 2, dot 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 dot. This is my sequence. And now from this step to next step, the p norm of this is nothing but sigma summation. I can write this quantity here as summation from n plus 1 till infinity, norm of xn p whole to the power 1 by p. But interestingly, this thing here was less than epsilon. So this thing here is less than epsilon. Why is it less than epsilon? It is less than epsilon because I know from my calculation above that this quantity is less than epsilon to the power p. So this to the whole 1 by p would be less than epsilon. Where did I get that this was less than epsilon to the power p? If you go just a bit up, we have proved this before. This is less than epsilon to the power p, and if I raise it to the power 1 by p, then it's less than epsilon. But now an interesting thing has happened. We took a sequence xn in LP and I approximated it with a degree of precision epsilon using a linear combination of elements from my set En, which means that indeed my space LP is separable. See you in the next proof.